So today we're going to talk about sampling distributions of sample means. So before reading the concept, the notes here, sample means, think about this here for a moment. We are dealing with multiple samples, and then we're going to take the means of those samples and form a new distribution. The reason is sometimes we don't have a normal distribution. So the formulas that we introduced last week, we cannot use them. One method, one technique to help us to get a normal distribution is to take random samples from that population and take the means of those samples, and then using those means as a random variable to construct a new distribution. Well, so let us begin. Here we have introduction. In previous modules, we used sampling distribution of sample proportions to estimate or test a claim about population proportion. Well, remember that we had confidence interval related to proportions. What we did, we had a sample, then we took a point estimate, p hat, which is the proportion in your sample. Then we said to construct a confidence interval, we need to find the error. Sigma sub p hat, which was equal to square root of p times 1 minus p divided by n. Then we needed to find the margin of error, which was for 95% confidence interval, it was 1.96 times our error, sigma sub p hat. Then the confidence interval was p hat minus the margin of error, comma p hat plus the margin of error. So again, sometimes we have samples, sometimes we have populations that are not normal. So what are we going to do? We're going to take multiple samples from that population, sample 1, sample 2, sample 3, and we are finding the means of these samples. The mean of the first sample, the mean of the second sample, the mean of the third sample. Then we're going to construct a distribution using these means. This is called sampling distribution of sample means. Try these. Election data for proportions. The data below, here we use a dot plot to represent the data that we have, shows the results from an election in an imaginary city like, let us call it city X or city Y. A computer simulation formed 200 samples of size 50. So we have 200 samples. Each sample has size 50. The sample size, or N, is equal to 50. A sample proportion was calculated. So it means that we have samples of size 50 and we repeated them 200 times. A sample proportion was calculated for each of those samples. The sample proportion represents the proportion of voters in the sample who voted for candidate A in that city. The collection of sample proportions in the dot plot is a distribution of sample proportions. So think about it this way. We have 200 samples. Each sample has size 50. Then what we did, we calculated p hat in each sample. Remember, p hat is equal to x divided by n. X is the number of successes, or in this case, the number of voters who voted for candidate A divided by 50. So p hat, or sample proportion, the number of people who voted to candidate A divided by 50. Remember that when we are forming a proportion, we have a fraction. So let me just make this here. Okay. So this is the dot plot that we have. On the horizontal axis, we have the proportion for candidate A. In different samples, we have different proportions. So take a look at these dot plots. It shows the proportion and how many times that proportion is repeated. So for example, take a look at 50%. 50% is repeated 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 times. So in 10 samples of size 50, 50% voted to candidate A. And by counting these dots, you can see how many samples. So remember that you have 200 samples. How many samples, for example, voted 60% to candidate A, and so on. So the question here is, what does a dot represent in this distribution? We have these dots. Each dot is on top of a decimal, or we can convert each of these into percentages. 50%, 55%, 60%, 65%, 70%, 80%, 90%, and so on. Each dot on top of these percentages or proportions. Again, we have 200 samples. It means that if we add all of these dots, if we count all of them, it is 200. So each dot here, what does it represent? Each dot represents a sample proportion. From each sample of size 50, we calculated the sample proportion, which is representing the number of people who voted to candidate A in each sample. So a dot represents a sample proportion. Each of these dots, again, if you add all of these dots together, it adds up to 200 samples. You have 200 samples. 1, 2, 3, 4, 5. Of course, we don't have enough space to represent all of these samples. Each sample has size 50. Then we calculated the percentages for each sample and represent it as a dot on top of each of these proportions. For example, suppose this sample of size 50 has proportion like 60%, 0.60. So this dot represents this proportion here. Again, you have 200 of these samples. Each has size 50. So now I expect you to ask, well, okay, you are giving us a new distribution. What is a typical value? If somebody asks me, hey, as a statistician, what is a typical value? What is a proportion of people in city X voted to candidate A? What is that proportion? What is that percentage? Well, in this case, we are looking for a typical value or the center of our data. What is the center? Remember that as a statistician, you're interested in assigning numerical characteristic to our data. What is the center? This is the next question that you should be asking. You collected the data. Okay, this is the data. This is the visualization of the data. But what's the meaning of that? What does it represent? What is a typical value? What is the center of the data here? So it seems like the center of the data, the balancing point, the typical value is located at 60%. So the center of the data is 0.60 or 60%. So the proportion of people who voted to candidate A in this city is about 60%. You can say that, hey, the center is around 60%. Very well. So now as a statistician, I expect you to ask, what if I change the sample size? In previous question, in previous sampling, the sample size was 50. So the sample size was 50. Now I expect you to ask, what if we change the sample size. What happens there? So let us take a look at two simulations here. So we're going to have simulation that was conducted 2 more times, but in this case, we are using 2 different sample sizes. So instead of having 50 people in each sample, we're going to once reduce that to 25 people in each sample. And then we're going to increase that to 100 people in each sample. We're interested in seeing what changes do we have for the distribution itself. Does it give me an accurate estimate of the typical value or not? Remember that we don't like to have too much variability in our data. We don't want variability. We want to have nice bell-shaped graph with less variability. Okay. So one simulation used samples of size 25. So N is now 25. And the second one, sample sizes are 100. So we're increasing the sample sizes. When sample size is 25, as you can see, the graph is like this. You have your distribution, which is like this. You see, you have variability. Starting from 40%, actually it's 35%, going to around 90%. When we are increasing the sample size to 100, we get less variability. It changes between 49% to 75%. So as you can see, we can for sure decide what a typical value is. Let's take a look at question 3. Which histogram do you believe represents samples of size 25? So of course, the first histogram, the first distribution, represents samples of smaller sizes. Why is that? Because we have more variability. The graph is more dispersed, more variability. More variability. And sample size is 25. Less variability. N is 100. So I expect you to conclude that if we increase the sample sizes, the graph gets narrower and narrower. Which histogram represents samples of 100? The second one. Explain why you think one histogram has a sample of size 25 and the other has a sample of size 100. The main reason is variability. More variability, smaller sample sizes, less variability, larger sample sizes. So you can answer because of variability. In our graphs. Okay, let's move on to the next page. And here we have election data. Now let us talk about the mean. Imagine that we want to examine the amount of time it takes someone to vote. Amount of time, it's not just proportion, we are measuring the time. We will call this voting time, and it is the number of minutes between the time when a person arrives at the voting station and the time when the person's vote is cast. Okay, so we have a new variable here. In fact, we would like to know the mean voting time. We're the statistician, we collect data. Now we're interested in finding the typical value or the center of our data. What is the average amount of time it takes a person to vote? To explore how we could find the mean voting time, we have created a simulation. Our dot plot here help us to visualize the data, understand the behavior of the distribution. Okay, 200 random samples were simulated. Each has size 50. So N, or the sample size, is 50. 200 of them were selected. The mean voting time was calculated for each sample. The voting time is given in minutes. The sample means are plotted below. Okay, this is our graph. Now, question is, what does a dot represent in the dot plot? You have dots representing the frequency of each of these dots on top of one of these numbers. So each numbers on the horizontal axis represent time in minutes. Each dot represents the frequency. For example, if you have 18 minutes, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 times 18 minutes is repeated. So each dot represents a sample mean. A dot represents a sample mean. In previous example, we had proportion in each sample. Here we have the mean time for each sample. So remember that we have 200 random samples. Each contained 50 people. We took the mean voting time in each sample. Mean voting time in each sample. Each dot represents the mean voting time in each sample. So these are the frequencies and these are the time in minutes. Question 5 says, well, now review the dot plot. Write down a single number that is your estimate of the mean amount of time it takes an individual to vote. It means that we're looking for a typical value. As a statistician, you have a data, you have a collection of data. What is a typical value? What's the center? What's the balancing point? Between 16 minutes to 20 minutes, which number balances this distribution? What is the typical value? If somebody asks you, okay, you collected the data, but what is the typical value? What's the number on average representing the time? Okay, it seems like if you look at the distribution, it seems like 18 is a good choice representing the center of the data, the balancing point. It balances the data here. So 18 minutes. Very well. So let's move on to the next page, answer more questions. The distribution represents many samples of size 50. Now, suppose you were to run the simulation again using sample of size 100. So what are we doing? We're increasing the sample sizes. How would the distribution of sample means from samples of size 100 be different from the distribution above? So as you know, since you're increasing the sample size, we expect to get less variability. So we expect to have less variability. So the graph should be narrower. This is our expectation. We are increasing the sample sizes, so we expect to have a narrower graph. Well, we have been plotting the mean voting times from all the samples. Suppose that you created a dot plot with the individual voting times of all 50 people in one of your samples, not the mean voting times, just individual voting times. In this case, each dot would represent a single person. How would this dot plot differ from that of the distribution of sample means dot plot? So think about it this way. Here we are collecting data, and then we are using a dot plot to represent the voting time for each person, not the mean voting time. So that's the difference between them. Individual voting times versus the mean voting times. Well, in this case, you are just measuring the time for each person. You're not calculating the mean voting time. It means that you get more variability. In this case, we just measure the voting time for each person. So we get more variability. So that's why we're interested in finding the mean instead of calculating the voting time for each person separately. So you can say that's the reason why we are more interested in finding the mean time for our distribution. Very well, let us try these. Collecting a sample. We will now continue our investigation of the sampling distribution of sample means. Again, note that we're not just working with samples. We find samples, we find their means, and then we construct new distribution. This time, we will use data about acorns that were gathered in Austin, Texas. This data can be found at the end of this lesson, the acorn mass table supplement. The students in Austin who collected this data were interested in acorns because they are the seeds of oak trees. In Texas, oak trees are important to the overall health of the ecosystem. Many birds and small mammals eat the acorns that come from oak trees. A decline in the growth of new oak trees could have a serious impact on local animal and plant life. So that's why it's important. So scientists are interested in knowing the weight of acorns. So what is important is the weights of them in a region. Well, they used information about the weight to answer some questions. So in the following exercise, we'll explore the data to estimate the mean weight. So this is our goal. What is the mean weight? So question 8 says, start by randomly selecting 9 acorns from the acorn mass table, and we're going to use a table of random digits or a random number generator to select the 9 acorns. Part A, write down the weight of each of the 9 acorns in your random sample. The weight is presented in grams, and B, calculate the mean weight for your sample of 9 acorns. Okay, so let us take a look at our data at the end of our lecture using these tables. So these are the tables that we have about the mass. The first one, the second one, as you can see the weight here. There are many of them, 400. So this is the table that we have. What are we going to do? We're going to use a simulation and then answer some questions. 10 random samples of 9 acorns were collected. The mean weight of each sample was calculated. These 10 means are plotted below. So on the horizontal axis, we have sample mean weight in grams, and each dot represent the frequency. If you have time, repeat the process of randomly selecting 9 acorns several times. Then calculate the mean weight for the sample, plot the sample mean on the distribution above, and write the value of each new sample mean below. So what are we going to do? We're going to randomly select some of these data here and then try to find the mean weight of them.